Hey guys, welcome to this video. Yesterday we had Codeforces Round 796 Division 2 and let's discuss the solution to the problems for the same. Let's start with problem A. So for problem A, we have been given an x and we need to find a y such that x and y is greater than 0 and x XOR y is greater than 0. Now this is an interesting problem. Arguably it's slightly difficult for an A problem, but let's discuss it. So let's just consider two cases. Let's consider a case where x is a power of 2. So if so in general, before I discuss this, one thing we need to understand is if x and y is greater than 0, that means there exists some bit such that both x and y are 1 in that bit. Now if both x and y are 1 in that bit, then for that same bit x XOR y will not give a value of 1, it will give a value of 0. So we will need like two individual bits, one which can give a value of for the AND bit to be equal to 1 and one which can give a value of XOR bit to be equal to 1. So if x is a power of 2, that means it just has one bit having value 1. So we will definitely have in y also for that same bit we would have to have a value of 1, since it is the only bit which has a possibility of making our AND greater than 0. So for example, if x is, let's say, 16, so 16 is something like this. So 1 2 4 8 16, yeah, this is 16. So for y we would definitely have to have 1 at this position, otherwise our AND would never be uh, greater than 0. But this same bit will give an XOR value equal to 0, so we would need another bit which is set for our XOR value to be greater than 0. So we will choose the smallest bit possible, so we'll just choose 1 here, and other bits we can just keep at 0 because we want the smallest value possible. So this is the value of 17. So what we can realize is that for every number x which is a power of 2, you can choose number x plus 1 as our answer. This is true for all cases except for x is equal to 1, because for x is equal to 1 we uh, the AND bit which we were setting was equal to the XOR bit which we were setting, so we cannot do both in the same bit. So for x is equal to 1, you can manually verify that the answer has to be 3. So if x is equal to 1, we print 3. Otherwise you can observe here that we would need the value x to match the AND bit, and you would need 1 to get another one for the XOR bit. Hence your answer for any power of 2 should be x plus 1. So let's just view the cases here which I've written in the code. So if x is equal to 1, your answer is 3. Now there are multiple ways of finding out if a number is a power of 2. You can use this trick that if the CEL of the logarithm of x in base 2 is equal to floor of logarithm of x in base 2, then the number is power of 2. Otherwise there is also another technique which is like if x and x minus 1 is equal to 0, then that's all, then also x has to be a power of 2. So you can use any of these. In such a case just print x plus 1. Otherwise if a number is not a power of 2, so if it's not a power of 2 and a number is not 0 because our number is greater than equal to 1, so it has to have like two set bits. Let's say these are the two set bits. So what we want to do over here is that we just have to match the smallest one bit to give AND as 1. And since we are not matching any of the larger bits, this automatically will give a value of 1 for the XOR, because we are not going here, we are just setting all of these to 0. So the smallest bit we will match because we want AND to be greater than 0, and other bits we will not match. So XOR itself will be greater than 0 because there are more than one set bits in the number x. Set bits are the bits which are set to 1 basically. So what we want to do is find the smallest one that exists in this number and then just give 2 to the power the number of bits here. So this is implemented in C++ libraries. It's just called as built-in count trailing zeros. So it's CTZ, count trailing zeros. And since I'm using long, I'll have to use CTZLL. So I'll just write it here. Okay. So you have to find out the trailing zeros in the number and then raise it to the power of 2. So it's basically 1 to the power of the trailing zeros. So I can basically verify it. Let's say my number is something like this. So what I'll do is just for the smallest one, I will match it with my own one. And since I have more than one ones, my XOR is definitely going to be greater than 0 because those ones are going to be carried out straight away in the answer. I hope you understand this. So, in implementation, it's just 1 to the power built-in count trailing zeros on x. So you need to understand one thing is that since x is long and it works, and since we are using bits here, there are like different functions. So you have to use built-in count trailing zeros ll for longs. Yeah, that's the answer. I felt that the problem was a bit complicated for A, but nevertheless, this is the solution. Let's move to problem B now. So in problem B, we are given an integer a1 to n. Yeah, a1 to an, and we are given two types of operations. One operation is that we can choose two numbers, let's say a1 and a3, and then replace them by a1 plus a3. Another thing we can do is we can take a number a2 and we can replace it by a2 by 2 or something like that. All of these can take like one operations, and what we want to do is find the minimum number of operations so that all of these numbers are turned odd. So let's consider this thing. Let's say we have one number which is odd, so a1 which is 3, and then we have something like 16, 32, 45, 46, 64, something like this. So even if one number is odd, if we just add all of the other even numbers to it, it will become odd, right? And so for each even number we'll just need one step, and we can prove that this is the lowest number of steps, because since these numbers are even if you divide them by 2, you would at least need one step. You would at least need one step to make them odd. But and here you are getting, for all of the even numbers, you are getting the answer in one step. Hence, this is the minimum number of steps possible. So in such a case, what we will do is, if there is at least one number which is odd, we will just find out the number of numbers which is even, and that is just the answer. That's it. So if this is not so, if we do not have one particular odd number, if let's say all of our numbers are even, so what we want to do is, we want to find the smallest number which is the number which has the smallest power of 2. Let's say there is a number which is like 2 to the power 10, and another is 2 to the power 11 into something, 2 to the power 12 into something. So we want 2 to the power 10. And we will divide it by 2 to the power 10. Like we will divide it by 2 10 times and finally get to an odd number. In this case it is 1. And once we get to an odd number, we'll add all of the even numbers to it. How do we prove that this is the best answer? This is because, let's say you do something else, you will at least have to make one number odd, and you cannot add it to any of the other numbers since they all have a higher power of 2. So if you add 2 to the power 10 to 2 to the power 11 plus a times 3, it still has a power 2 to the 10 a power of 2 to the power 10. So you would at least need 10 steps to, if you make any sum, you would at least need 10 steps to make it odd. So here we are just using 10 steps to make it odd, which is the lowest possible. And once we make this number odd, we can use the same strategy that we used earlier and add all of the other even numbers to it. So our answer would be the smallest power of 2. So if the power of 2 is 3, you would need you would need 3 steps to make it odd, and then you just find the number of numbers which is even, and in this case like all of the numbers would be even over here. So it is n minus 1 plus smallest power. Now how do we implement this? So basically we just want to find out how many numbers exist with what power. So for that what we will do is we will store it in an array or vector. Like you can also have just a number to check which is maximum or minimum, but I just made an array over here because I wanted to think quickly. So in this array B, the element at bith position represents how many numbers are divisible by 2 to the power I, but not divisible by 2 to the power I plus 1. So it is like the largest power. So what I do, for each number I maintain a variable x, and every time it gets divided by 2 I increment x, and finally I just increment the value of b of x, because this number is divisible by 2 to the power x. And finally, if there is at least one odd number, then your answer is just n minus b of 0. N minus b of 0 is basically the number of even numbers here, because b of 0 is the number of odd numbers. But if there is no odd number, I start iterating through this vector to find the smallest power of 2 which has at least one element which is divisible by that. So for example, I want to find out, let's say I have like 8, 16, 32. So I want to find the smallest power of 2 which divides one of the particular number, but which is the highest divisor for that number. So for example, for 8 I want 8. Let's say it were like 24, also I would want 8, because it's like the largest power of 2, which divides 24. And it's the smallest power of 2, and its smallest such number for all of the integers. For example, like for 16, it's divisible by 16, 32 is divisible by 32, but for 24, the highest power of 2, which is divisible by 2, is just 8. So we want the smallest of such powers. So that's it. So once we find such a number, as I said earlier, it's just the smallest power, which in this case is I, and plus n minus 1. So answer is I plus n minus 1, and we just break here because it is that this is the answer, this is the smallest answer that we will have, and then we just output this answer. This is a solution. I hope it's clear.
Hey guys, this is Tahir from Programming Club IIT Madras, and today I'll be explaining the solutions to problems C and problem D of today's Codeforces Round 796 Div 2. So basically, in problem C, like the player starts off with a string of initially of length 1, and he follows a sequence of n operations, where in the ith operation he replaces the substring t2i minus 1 of s with t2i, and kind of after following all this whole procedure of n operations, we end with some other string, some other string s, and t is basically a sequence of 2n strings. So then after this, the whole sequence of strings t gets shuffled, and we also forget what the initial string we started off with was, but we know the string that we end with. So we're supposed to find the string that we basically started off with. So like here in the input, we're given an integer n, and then we're given a sequence of 2n strings, which corresponds to a shuffled version of t, and we're given the final string, which is like the final string after applying all these operations. So basically, if we follow this example here, we can start off with A, and we can replace A with AB. So then these two, A and AB, are kind of done in the sequence T. And then after that, we can replace the B. Currently we have AB. In AB, we can replace the B with CD. So we get ACD, which is the final string that we want. So hence here we started with A. So the answer to this would be A. And in the second example, similarly, we can start from Z, and by kind of mapping some of these strings to some other strings, we can end up with this final string starting from Z, and hence the answer here would be Z. So basically, in this question, like the key thing to notice is to kind of check the parities of every character in the initial sequence T and in the final string S. So basically, if say, mm, so in this question itself, what we can do is we can kind of note the parity of each character in the sequence T and in the final S. So here, basically, Z appears just once. Maybe I can write it down here as well. Z appears once, and A appears 1, 2, 3, 4, 5, 6, 7 times. Similarly, we can see Y appears twice if we include the final string S as well, according with all the other TIs. Y appears twice. And then what else? K also appears twice, U also appears twice, and M also appears twice. And similarly, O appears twice, R appears twice, and N appears twice. Basically, see that out of all these characters that appear in the sequence Ti and in the final string S, uh, I think I made a mistake here. A actually appears 1, 2, 3, 4, 5, 6, 7. 8 times, not 7 times. So I'll just cut that. So basically here what we can notice is all of these strings appear an even number of times, whereas uh, the character Z appears an odd number of times. Similarly, if we say look at the first example, A appears 3 times, B appears twice, C appears twice, and D also appears twice. So in this example, A is the only character that appears an odd number of times, whereas all the other characters appear an even number of times. And here also we notice that the final answer is here A, whereas here the final answer is Z. So basically here what we can note is like for every character that kind of comes in between the sequence but does not appear in the final string, it must have at some point whenever it was introduced into the strings, like let's consider the character A, or for this example itself let's consider the character or let's just say that in some sequence of operations the character A appears in between but the character A does not appear in the final string. So in that case A would be generated from say some other string, like the character A would appear in some string. Okay, let me label them, like say some S1 gets converted to some S2 in between this set of operations. So if some character A appeared in the sequence of operations, then let's say S2 was the first time it was introduced. Then later on, if in the final string S, A does not appear, then that A would have later on been in the LHS of some other operation, and hence it would have disappeared. So every time some new character appears in the string, if it's not there in the final string, then it should also disappear later on by being in the LHS of some operation. And hence, every character that does not appear in the final string S would appear in the sequence T of 2n strings an even number of times. Whereas every character that might appear in the final string S would would in like in between the sequence of operations it might come in and come out a couple times, but in the end that it'll always end up in some RHS and it won't be in some LHS of some operation later on, because that string is like that character is kind of conserved in the string. We want it to be in the final string S, and hence it would appear an odd number of times because it would appear one extra time in an RHS than it would in an LHS. But this, of course, excludes the initial character that we start off with, because that kind of is never produced from something else. We start off with that. So that appears one extra time in the beginning itself, not counting these kind of operations. So hence, every character that is in the final string would appear an odd number of times in the sequence of strings T, and hence if we include the final string as well in checking our total parity, that character would appear an even number of times. Similarly, every character that finally appears in the final string S would appear an odd number of times in the sequence of strings T, in which case, if we again include the final string S, we would have the total parity of that character to be even, except for the initial character that we start off with, because that would again not appear in any that would not appear as an RHS of any kind of operation here. So that will appear like one extra time, and hence that will be the only character to appear an odd number of times. So what we can do in this question basically is just if my I can just load my code. So we can have an array which keeps track of the total number of times each character comes in the sequence t and the final string s combined. So what I do is for each string ti, I run a for loop and I increment it every time it appears. And similarly for the final string s, I run a for loop and I increment the count corresponding to that character every time it appears in the string. And finally, in the final for loop, I check for all the counts, and whichever counts are even, I would just ignore them. And if any count happens to be odd, then I know that that must have been the initial string that we started off with. So if ai mod 2 is equal to 1, then char c is equal to I plus a, which is just like shifting because of like ASCII values, and then I'll just print that string and return. So, like I'll just print the character and return. So that's basically the solution to problem C. Now, as for problem D, we are given n points on an x-axis, which are numbered from 1 to n, and we are given an array a1, a2, an, and basically we can move from any point x to any point y if y is either adjacent to x or y is equal to x, that is mod x minus 5 less than equal to 1. So then basically what we do in this question is just a second. So basically what we do in this question is we can start off at any point, and these values a1 to an correspond to like some number of mushrooms at the point uh, I, like AIO corresponds to the number of mushrooms at the point I. And basically, at every iteration, we start off at any point, and at every iteration, we can move from a point x to a point y if y is adjacent to x or y is equal to x. We collect all the mushrooms at the destination point y, and a new mushroom appears on every point in the whole number line. So we have to find like a sequence of moves that we can start anywhere that basically maximizes the total number of mushrooms we have at the end. Um, and also we can repeat points as well. So we can kind of we can kind of wait for more mushrooms to grow at a point and kind of recollect them. So here we are given the input n and k, where n is the initial number of points on the number line and k is the number of iterations we can go through, and we have the array a1 to an. So basically here in this question, the key kind of observation is, okay, so if I'll just draw a number line, let's say this point is 1, 2, 3, dot dot dot, this point corresponds to n. Basically one key observation in this question is, like, let me consider the point 3. If I were to ever come to the point 3 and like collect all the mushrooms from there, and if I kind of went somewhere else, I kind of explored, went somewhere else and came back to 3, and some number of mushrooms grew in 3 again, so I collect the new number of the new mushrooms that grew at 3 since when I left, and then again I kind of go somewhere and come back to 3 a third time, and again I collect all the mushrooms at 3. That is basically equivalent to kind of ignoring the mushrooms in the first and second time, just not collecting them, and collecting them all at once when we come the third time, because the number of mushrooms will still remain the same nonetheless, whether we collect them or not. So if we collect them in one after the other, or we collect them all at once, it doesn't really matter. So if I am ever going to repeat a point, I can kind of ignore taking the mushrooms the first time and instead take it the second time later on. So that's one key thing to note. So here basically we can divide this problem into two cases. One is when k is less than or equal to n, and one is when k is greater than n. Okay, so if k is less than or equal to n, then there's no way that we can ever visit all points, because we need at least k is equal to n to visit all points. So in the case when k is less than equal to n, the optimal way to kind of maximize the number of mushrooms you can take is to kind of visit distinct points in each iteration. You never want to repeat a point, because if you repeat a point, that's equivalent to kind of ignoring it the first time, which would kind of waste an iteration. So, like, let us say we start at some I, at like the ith point, or I'll just draw it here. Let's say this is the ith point, and this is some I plus k minus one point. So basically, if I start at the ith point and I go rightwards, every iteration I go one step to the right, then I can take all mushrooms from points I to I plus k minus 1, including the new mushrooms that might also grow later on. So I can kind of check this for all I in linear time, which one leads to like the maximum uh, number of mushrooms. So basically, if I were to start at the ith point, I can initially take AI mushrooms. And then in the first iteration, a new mushroom would have grown from I plus 1 to I plus k minus 1, and also at every other point as well. So in the second iteration, I would take a I plus 1 plus 1 mushroom. And then in the third iteration, I would take a I plus 2 plus 2 mushrooms. Dot 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 until a I plus k minus 1 plus k minus 1 mushrooms. So this sum would basically be equal to the total sum. I'll just call it sigma A j, where j goes from I to I plus k minus 1 plus k into k minus 1 by 2, because the summation from 1 to k minus 1 would just be k into k minus 1 by 2. This is basically a constant, but this summation varies from depending on I, because it starts from I and it goes till I plus k minus 1. So what we can do for the k less than equal to n cases, we can just start with we can just kind of create a prefix sum. I just name the variable sum. Whereas the sum of I would basically store the total sum of all AIs from like sum of I would store the sum of all AJs from j is equal to 1 to j is equal to I. So that's like a prefix sum. And for k less than equal to n, I just set my answer to some very low value. Let's just call it minus infinity. And for int I is equal to 1, I plus k minus 1 less than equal to n I plus plus, what I do is answer is equal to maximum of what the answer I found so far, comma, sum of I plus k minus 1 minus sum of I minus 1 plus k into k minus 1 by 2. This is just the prefix. This is just like the sum of all the mushrooms that were initially there at these points, and this is the total mushrooms that I get, which kind of grow over time over all the iterations. So the maximum over all I of this expression is basically our answer for the k less than equal to n case. Now what about the case when say k is greater than n? Basically for this case, I can basically cover each and every point. I don't like there won't be any point that I can't cover because of the constraint in number of iterations. So in that case, what I could do is, again, as I've mentioned, if we ever come to the same point multiple times, we can always ignore taking mushrooms the first couple times and we can just take it the last time. So for k minus n of the iterations, we basically don't need to do anything. We can start off at the first point and we can stay at the first point itself, and we can like never move. That is fine. But in the last n moves, what I could do is from the first point, I could for the first iteration or the k minus n plus 1 iteration, I could go from 1 to 2, then 2 to 3, and so on, and then from n minus 1 to n. Like that's the optimal way to maximize the number of mushrooms. Even if in the first k minus n turns, I from 1 I were to go somewhere and then I came back to 1, that would be the same as staying at 1 for the first k minus n iterations and then going from 1 to n, because again, if I come to any point twice or thrice or like multiple times in my set of moves, then it's equivalent to just taking mushrooms only the last time and ignoring it the first few times. So I stay at 1 for the first k minus n turns, and in the last 10 turns I will go from 1 to 2, 2 to 3, dot dot dot, n minus 1 to n. So then how would we calculate the total number of mushrooms that we can get in that case? So basically, if I stay at 1 for k minus n turns, then the total number of mushrooms that would grow at the point 1 over those k minus n turns would be, like, initially that would of course be the A1 mushrooms that we initially had, but on top of that you would also grow um exactly k minus n mushrooms. So and then later on when we go to the second point, we would have waited one extra iteration after, in which we were kind of taking the mushrooms from the first point. So we would have k minus n plus 1 extra mushrooms at the point 2. And if we kind of keep following this sequence, at the nth point, we'll have an plus k minus n plus n minus 1 mushrooms, which is basically just k minus 1 mushrooms. So the final answer will just be a summation of all these terms. So again, this sum is just can easily be calculated in constant time using that prefix sum that we had calculated, and this sum is just the sum of the sequence, which can just be like the total sum from 1 to k minus 1 minus the total sum from 1 to k minus n minus 1, which can be calculated easily. So in the k greater than n case, that's in the else case, I just put int sum is equal to sum of n is just the sum of all ai's from I is equal to 1 to n, and then I add that summation that I've calculated. Uh, and that will be our final answer. So that's basically the solution to the part D.
Hi, I'm Teja-Smart. I will be explaining Codeforces Round 796 E question. Now, railway system. Uh, about this, it's some story. We can ignore that normally in context. This is an interactive problem. Interactive problems. Normally, in the problems, we will take the input and then we will give the output. Like these are two different steps, right? Like we need not do something while taking input, like take input, send output something, and then take input and send output something. Like that, we just get a question and then we will output something. The interactive problem is like we will keep exchanging information between us and the computer. That's why it's called like interactive, because it's like we are interacting with the GD or computer. Uh, so it's called interactive problem. Means the main difference is here we will also be uh, after after getting some information, we will also be sending some information, and based on that, it will give us some other information like that. So these kind of problems are also a little bit different, because it's like it's about the information we ask, what we ask, is will be important, and what I mean we have to make the process based on what we ask. Like I mean we should think about what kind of questions we will ask so that we can get an answer, so that we will be able to solve our question. Okay. Under the direct supervision of Kanako and Moria Shrine, the railway system of Gensokyo is finally finished. GSKR, Gensho Railways, consists of N stations and M bidirectional roads connecting them. N stations and M bidirectional roads. Bidirectional tracks. Okay, tracks. The eighth track has length Li. It's less than 10 due to budget. So there are N stations and M tracks. Maybe it looks like some graph question. So I mean there would be some edges, but let's see completely. Due to budget limits, the railway station may not be connected. So it's saying that the given graph may not be connected, though there may be more than one track between two stations. This is not very common in questions, but okay, here it says that there can be more than one track in two stations. About this question, as I have already solved it, I can say that it looks tough. I mean, not tough. It looks big. Like the only uh, why people solve it less, because people will have given up by after achieving till there, because uh, they may be thinking that this is tough and they will have left it. But I guess uh, it's it's if we just read it, then if it's just read it and we have the knowledge of something, then we can solve it. It's very easy question only, I guess, if we have the knowledge, and if we don't leave it without trying. That's the two main things are required for this, like a little bit of knowledge and without leaving it in the contest. Those two are the important things. Okay. I'm saying this because I already solved that. The value of a value of a railway system. So now this railway system, which has n stations and m bidirectional tracks, has some value. It seems that value is defined as the total length of its tracks. Okay, the maximum or minimum capacity of a railway system is defined as the maximum or minimum value among all current functional systems. Full spanning forest. In brief, full spanning forest of a graph is a spanning forest with the same connectivity as the given graph. Okay, let's see, as they have given here full spanning forest, let's try to see it. Okay, I can say, I will explain it in sideboard. Oh, yeah. So now, uh, let me say some small basic things about graph theory. Maybe like uh, a graph, maybe a graph would be will be having some stations. Here it's stations, and then some edges. You can just think of it like this: some edges and some vertices. That all it may not be connected. Connected means now this and this are in some way, in some sort of way, they are both are not connected, right? Like that's called that's what they're given here, like by saying may not be connected. Uh, Now we can think of here we can think of prerequisites for this. I will okay. And then okay, we can just think of it like that. These graphs may have cycles. Like here we can see a cycle, like come here, come here, come here, come here, like that. And they may not have cycles also. Now a tree is a graph with no cycles and which is connected. Like these kinds of things are called trees. I'm just saying this definition because I don't want to say anything related any basic graph theory. I just I mean even I was I mean we have to recall this to understand what a full spanning forest is, right? Because it was given in the contest directly. I don't know what a full spanning forest before. I mean, before the contest very clearly. That's only they also gave a link. So I'm just recalling it for myself or for you also. Uh, this is a tree. This kind of things are called a tree. So any graph can, by removing this, it may become a tree. But we can also remove this. It will be some other tree. So these are called trees. So I told that a tree is a graph which is connected and which does not have any cycles. So there can be a graph which do not have any cycles and which may not be connected. So if you take this whole as a thing, so this is a graph which is not connected because there is a break here. Not, we cannot call it break maybe, because these components are not connected and they don't have cycles. These kind of things are called forests. So we know trees because this can be tree has some two trees. So many, if there are more trees, we can call it forest. So it's that's what forest. Now a spanning tree is a tree which goes through all the vertices. It's a tree in which all the vertices are there. Oh, wait a minute. Uh, a tree in which all the vertices. But spanning forest, uh, uh, spanning forest may not be unique. Not it's not just that. Okay, let's think about spanning forest for this. For this spanning forest, if a spanning forest can be removing all the edges, then everything will be a single dot, 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 like that. This is also a forest because this itself a tree because it's connected. It's connected and it does not have any cycles. So all of these are trees. So even it's a forest. But this forest loses the connectivity property because here these two are connected. Here these two are not connected. By this, that's what they meant. We need a fully spanning forest. So every vertex should be in some tree and the connectivity should be maintained. So if these four are connected in the main graph, in our spanning forest also, they should be connected. So it should form a tree and they should be connected. So it will be like something like this. Yeah. So here I am removing this edge. I'm removing this edge, then it will look like this. It will look like this. So it's a tree now. Also, this is a tree. So these both are trees. So it's a forest now, spanning forest. That's what they meant by spanning forest. Also, this is spanning forest, but they told the connectivity should not lose. So here the connectivity is not losing, and it's a spanning forest. This is what they mean by spanning forest. Um, and now this, so many then would many spanning forests would be possible for a single graph because here we can remove either this or this or this. So multiple would be removed. What multiple things would be possible? Multiple spanning forests. In that maximum or minimum capacity, we can define something like maximum or minimum capacity based on the maximum or minimum value among all the current functional systems. So I told that there are many spanning forests that are possible, right? We can value of a spanning forest is sum of all the edges, and so we'll get different values. So the minimum value and maximum value is called minimum capacity and maximum capacity. These are the definitions. Those are simple only, I guess, till now. And then I think the from now the question is easier only. The main difficult part was to understand what a spanning forest is. If we leave at this point, we cannot solve the question now. So I think till here it's tough. And then if you see, Kanako has a simulator only able to process uh, the simulator. Okay, he has some simulator which can only process 2M queries. Means we can ask it 2M questions. We have to see what kind of questions we can ask also. The input of the simulator is a string s of length m. So we will give the simulator a string s of length l consisting of only zeros and ones. It seems the simulator will assume the ith track functional if si equals to 1. So it will assume if si equals to 1, it will take the track as functional or else it will take as not functional. It seems the device will tell Kanako the maximum capacity of the system in the simulated state. So some are stimulated, I mean some are functional, some are not functional. So it will say what is the maximum capacity of the system for these kind of functional things. Like, I mean, we will select some edges and we will say only these edges are functional. So it will say maximum capacity for that. So we can ask various questions. We can ask 2 power m different questions, but we are only allowed to ask 2m questions. 2 power m because there is string of length m. We can change zeros and ones and we can ask 2 power m, but we are only allowed to ask 2 into m. Tanaka wants to know the maximum capacity of the system with all tracks functional with the help of. Now they want minimum capacity when all are functional. Okay, this is the question. This question we need to answer. Normally, minimum capacity of the forest is nothing but like minimum spanning tree question. So we can also take another one question. One is basic definitions of graph theory prerequisite. Another prerequisite is Prim's algorithm of minimum MST algorithm. Prim's algorithm. I'm not sure if it's Prim's. Kruskal. I think it's Kruskal. Wait a minute. Control and Yeah, Kruskal's algorithm. Sorry, it's I should not say wrong here. It's Kruskal's algorithm. For this question, maybe you can also use I don't know. Prim algorithm will be difficult here. Kruskal algorithm, which is keep on adding the weighted least weighted edges, uh, as long as they don't form, not as long as they don't form a cycle. If they are not forming a cycle, add them or else skip them. Like this, we will form a tree. That's Kruskal algorithm. Those two are prerequisites, like basic definitions of graph theory and this Kruskal algorithm. If you just know both of these, I think then the question is direct. I mean, we will get to know that it's direct later. The structure of the relay system is fixed in advance, so the relay system is fixed. Okay, we can ignore that. The first and the only line integers, only input. First line of input contains only two integers, n and m. N means number of stations, m means number of edges. Okay, the number of stations and tracks. So they are not giving any fixed edges. So this makes our question simple because it only has inputs n and m, nothing else. And we are all just 2m questions. So I think this makes it simple. Now begin the interaction by reading. It has a lot of text. To explain the text only, it's taking a lot of time. Begin the interaction by reading n comma m. Okay, first we have to in the interaction. First we should read two integers n comma m. To make a query, we should print question mark space s. The s is a string of length m. Before if we keep once, it assumes that those edges are present, and then it will give us the maximum spanning forest. There is something like a spanning forest for a graph, right? They will give the maximum. There is something like capacity. The definition that it's there in the above. We need not. We will try to think about this little bit if they are useful in the question, or else they may not be useful in the question also. These definitions, because uh, then you should read the maximum capacity of the system is in the simulated state. Then we should try to take an integer input. The input consists of maximum capacity of the state in the simulated state, maximum capacity of the system. Okay. If your program has made any invalid query, we can ignore this for now maybe because it's only if we do any wrong thing. Let's assume that we are not doing anything wrong. To give the final answer, okay, if we should find this is our main aim, minimum capacity of the system. We should find it. Okay, print this one. L is the minimum capacity of the system with all tracks functional. Note that given the answer is not counted as counted towards the limit of query queries. We are outputting this now. This is not a query. The question mark thing is only query. That's what they're saying here. Okay. After printing a query, sometimes we need to flush the output. I don't know why. I think it's like they will be in the stream or somewhere. If we flush them, they will not be there and it will be clean. So we can do it well, I guess. Okay, now the question looks simple. Let me explain this thing. Suppose if this is the system, this is the graph. So when they ask this question, when we ask this question to the computer, what should it say? All zeros means all of these are inactive. So all no edges are there. When no edges are there, the answer should be capacity should be zero. So it gives zero capacity. And then when 1, 2, 3 are 1 and fourth one is 0, if 1, 2, 3 are 1 and this is 0, then maximum for maximum 3 it will take 2, 3. It will remove this and it will take 2, 3 and it will give the answer 5. Okay, that's also easy. If all 4 are present, then also it will remove this one and then 2 plus 3, 1, 3. This is another tree. This is called spanning forest. So it is 4 plus 5, 9. 9 was given, and then we are removing this thing third, then it will be 3 plus 4 7. Okay, so the 7, and then that's the best, that's the minimum thing, because removing this will get a mst in this tree, in this component, and this is already a minimum spanning tree. I think that's why it's like that. Okay, now uh, like it's a bit complex, right? What they are saying is they will give us maximum spanning tree. I don't think we know anything about maximum. Okay, let's try to think of what a maximum spanning tree is. Okay, I'll explain prim algorithm for minimum spanning tree, like for this 1, 2, 3 on this thing. Prim algorithm is, sorry, it's Kruskal algorithm. Kruskal algorithm is assume that there are no edges and there are only vertices, and then add the least edge 1. This is not forming a cycle now, so add it, and then add the next one 2. Also, this is not forming a cycle now, then so we can add. And then when we are adding this 3, it's forming cycle, so we cannot add it. This is the algorithm, so we should not add it. And then this algorithm will surely form a spanning forest that we can prove that you guys can try to prove it separately by learning this algorithm for graph. The correctness of this algorithm also, that this is the best way to do. This is the minimum thing. That also we can think. I mean, try to you can try it because it's related to Kruskal algorithm. I just explain how to use an algorithm. Okay, this is what the algorithm is. Oh, okay, this maximum capacity that they give is a bit complex to think about. For that, I think Kruskal algorithm may work in other way, like start from the maximum thing. I mean maximum edge and add it 4. I mean here we are going 1, 2, 4, 3, 4. Now here I think we should go reverse. I mean these 1, 2, 3, 4 are weights. I mean they are weights. Now add 3. Now add 2. I think this would be the maximal capacity. I think the reverse of the I mean same Kruskal algorithm but sorting the edges in opposite order and running them. Running them means and adding them. I think this will give the maximal capacity. I think even this is complex because how can I think in this way? So let me use this maximal. It will give the maximum capacity, but let me use that to only find the edge values. So if I keep everything else non-functional and keep only one edge as functional, what the simulator will return me? It will everything else only one edge is there and everything no edges are there. So all of them will be disconnected and only this will be there. If there is a forest, the forest will be only having this edge, and it must have this edge because it should satisfy this connectivity property. So it will return the sum of all the lengths. One there is only one edge, so it will return that length. So if I do that, I will be using how many queries? M queries to find the values of all M edges. So I will use M queries to get all values, all edge values. So if I have all edge values, we can use the Kruskal algorithm by sorting edges and adding them one by one uh, to make the MST or to get its value. If you know what all the edges we added to the MST, the value of the minimum spanning tree, which is minimum spanning forest here, will be the value, the sum of all the edges that we added. So we are not making the tree, but we can know its value. If we know what all the edges are present in MST. So now I got all the edges and I have asked M questions. So I am only left with, so I'm asking M questions. I don't know each question is, I will keep only one edge as active and all edges are inactive, means 0, 0, 0 and 1 M, 1, 1 and 0, 0, 0. And then it will return me the value of the edge. I have explained it just now because if there is only one edge, that's the max, that's the only spanning forest and that's the maximum capacity of the spanning forest. So it will return the value of it. So we got all the values of edges. We are not sure that this will work. Now we can solve using Kruskal algorithm. But let's see if it works. Then the question is done now. So okay, now let's assume that we have sorted the edges. After sorting the edges, let me add edges one by one. Same Kruskal algorithm. And now the thing in the Kruskal algorithm is when an edge comes, let us say these are 1, 2, 3 weights. And when an edge comes and it is forming the cycle, we should not add it. That's the Kruskal algorithm. Let's see. So at any point, if we take Kruskal algorithm, it will be like a spanning forest. It will be like a spanning forest. I mean, there won't be any cycles in Kruskal algorithm. In our if we after adding some edges, we are in the middle of Kruskal algorithm, then it won't be there won't be any cycles because if an edge that we are adding form cycle, we are not adding it, we are skipping it. So inactively there won't be any cycles in Kruskal algorithm at any step. So there are no cycles. So if there are no cycles, the spanning forest must be unique because it respects that connectivity or something. So it will be unique. So if we add this, so now this is, let's say, I'll draw it again. Let's say first we added the 1 and then we added 2. Okay, here there is no problem, and then we have added 3, also no problem because there is no, and then let's say this is 4 and we added 4. Now there is an edge 5 that will add here. We should know that, we should be able to know that if 5 will add here or not. We don't have the graph. We can only ask about the maximum capacity and maximum capacity of some functional edges. So we don't have the graph. So let's see if we put this 5 and ask for maximum capacity, what will happen? Suppose if we put this 5 and ask for maximum capacity, it will remove one of these positive edges. So it will return, let us say till now we have some kind of sum. let's say the sum we have till now is val value. I mean, so after adding this 5, it will be val. It will remove this one and it will give this as maximum capacity plus 5 minus 1. This will be uh, let's say this is E. Here E equals to 5, which is greater than which is forming a cycle. It will be E minus 1, or else that will be minimum. Okay, let's say it is 1 only. Uh, okay, if it is not forming a cycle, then what will happen? Suppose this is the tree and it is adding here. If it is not forming a cycle, then it will be val plus E. Nothing will be subtracted here because as here a cycle is forming, for maximum thing it's removing this minimum and it's increasing its value because we can remove any of these H to form a tree. We are removing the smallest one to get the maximum capacity. Okay, so if it is not forming a cycle, it will be val plus C. If it is forming a cycle, it will be val plus C minus 1. So using these two things, we can differentiate for an edge if it is forming a cycle or if it's not forming a cycle. If you can just do that part, that's enough to find the crystal algorithm, right? We will keep on adding the edges and we will have to check if it's forming a cycle. For that, what will we do is we'll be having the value till now of the edges that we added. That is the spanning forest till now. And then after adding an edge, we'll we will request for the maximum sum. They will return and then we will check if the value is if it is equals to val plus e or not. If it is equals to val plus c, that means we can add it. If it's not equals to val plus c, then we should not add it. We will skip it. So in this way, we are able to use critical algorithm. So for each edge, we are here. This so something I written just so this will take a query. Yeah, we are asking for maximum capacity of the tree after adding this edge, right? It will take a query. So at max, we are taking here also m queries, and not only at max, we are surely taking m queries because we have to make sure that every edge is not forming a cycle. Every edge that we are adding should not form a cycle. For that, we are adding that edge to the minimum spanning forest that we have processed till now, and then we are checking uh, and then we are getting the maximum capacity, and then if we are checking the maximum capacity equals to val plus c or not. If it is val plus c, that means it forms a cycle. If it is not val plus c, then it forms a cycle. I think as there are no zero edges, I mean length is not zero. I think it's working well. I don't know if the length is. I don't know what happens if the length is zero. Uh, so in this way, we can differentiate if an edge forms cycle or if it doesn't form cycle. If we are able to know if an edge forms cycle or if an edge doesn't form a cycle, then we can complete the critical algorithm, and then we know what are all the edges that we added. If you are adding an edge, we will increase the value because the new value will be val plus the new edge. So in this way, we can use the critical algorithm. If we are able to use the critical algorithm, then we have completed the algorithm and we got the minimum spanning forest or minimum spanning tree. Critical algorithm can be both used to find minimum spanning forest and minimum spanning tree. So yeah, now we got the minimum spanning, the cost of minimum spanning forest. The final value of val will be the cost of minimum spanning forest because we applied the critical algorithm completely. So we should be having the minimum spanning forest. I think that's it. I will explain my code if it's near. So I'm taking the input because it's told to take an input, and then what I'm doing is I'm using m queries to get the weights of all the edges. So what I will do is mm, what I will do is I will for each of the thing I will just output j equals to I means it will give 0 if it is not the edge that we are considering now, or else it will give 1. So there is only one edge active, and then I'm taking an input. In this input, it will give the maximum capacity for this. Oh, maximum capacity. That's the edge length, right? I'm storing it in a of I, and now I should sort. After sorting, the indices will be lost, right? That's why I'm storing them as space to save the indices. I mean, to keep the indices alongside the values. After sorting, I may set this sort to get the wrong answer. Okay. After sorting, now in this status, I will keep the status of the edges that I have added to the minimum spanning forest till now, because I'm now performing the crystal algorithm. I will keep adding edges. Some edges we should not add because they form a cycle. We'll just skip them. So till now, if I am adding some edges, I'm keeping them in this thing, because what we are giving to the system is, I told what we are giving to the system is the minimum spanning tree plus E. The minimum spanning tree plus the edge that we want to check, that all of this we are giving. So we should keep once for all of this and this for this E. All of that we added till now and this E. So for that I'm using this ST. Uh, if j equals to a of I dot second, means the current processing thing, then we should give 1, because we have to activate this. All of these are already active. We are activating this and we are asking for answer. So after asking for answer, if it is equals to value plus a of I dot first, that is nothing but value plus e. If it is equal to this, then we can add that edge. For adding that edge, I'm doing val plus a of I dot first, and then I'm keeping the status equals to 1, because status means it's like it got added, then it's 1. Else it's 0, because it's not added and we are skipping it. So after the end of this, as I told, the value will have the value. So I'm just outputting the value. That's it. I think this is enough for this. The main thing is like they have given complex things like maximum spanning forest, but we haven't used it for anything. We use it half of the queries to just know the values of edges, half of the queries, and the other half is also just to perform the direct critical algorithm. To perform the critical algorithm, we have used the other images. So I think it should be. It's complex in terms of its words and definitions that are involved in the question, but after we just use them to get the edges and then to see if there is a cycle or not. Okay, I think this is enough for this. Thank you.